Bismillahirrahmanirrahim. Assalamualaikum, students and physics enthusiasts. One of several applications of light diffraction is measuring the thickness of very tiny objects such as a human hair strand. Join me as we revisit a past upload on single-slit diffraction of light. Just sit back, relax, watch and learn. Problem is, from actual laboratory measurements on a human hair, it is found that when a beam of light of wavelength 632.8 nanometers was shown on a single strand of hair and the diffracted light was viewed on a screen 1.25 meters away. First dark fringes on either side of the central bright spot were 5.22 centimeters apart. Question is, how thick was this strand of hair? So, as illustrated in figure 1, the type of light diffraction that we are going to discuss is the so-called Fraunhofer diffraction. Diffraction occurs when light passes through an aperture or around an edge. So when the source and the observer are so far away from the obstructing surface that the outgoing rays can be considered parallel, it is called a Fraunhofer diffraction. So the light source is a monochromatic wave, right? An example of a monochromatic uh, light wave is a laser. So when the light waves emitted by the monochromatic source pass through the single slit, right, or a very narrow opening, okay, uh, when they reach the screen, right, um, they form alternating patterns of bright and dark fringes, right? So the central bright band or bright fringe is, of course, the brightest. All the brightest fringes are the results of constructive interference, while the dark fringes are the results of destructive interference. In this problem, we are given the wavelength of the monochromatic incident light denoted by the Greek letter lambda, which is equal to 632.8 nanometers. The distance between the slit and the screen, denoted by small letter x, is equal to 1.25 meters. And the separation distance uh, between the two first order minima or first order dark fringes, denoted here by capital letter Y, all right, is equal to 5.22 centimeters. All right. So may I emphasize the meaning of capital letter Y is the distance between uh, the two dark fringes, or that's also called uh, dark fringes are also called minima. In this case, we're talking about the distance between the first minima, all right, on either side of the central bright fringe. So that's equal to 5.22 centimeters. So notice that in Fraunhofer diffraction, the value of x is considered much greater than the value of y. So our target variable is the thickness of uh, the human hair strand used in the experiment. So we denote that by small letter a. All right. So a similar result holds when light bends around a straight thin object such as a strand of hair, in which case a, or small letter a, okay, is considered the width of the hair strand. So may I say that again? In this problem, small letter a represents the thickness of a human hair strand, which in the usual single-slit Fraunhofer diffraction experiment, that corresponds uh, to the width of the slit or the opening, right? So for the first minimum or first order minimum or dark fringe on either side of the central bright band, from the center of the central bright fringe, all right, that is represented by capital Y sub M, right? That is just equal to capital Y, which is what is given in the problem, divided by 2. So, may emphasize that once more. What is given in the problem is capital Y, right? Which is the separation between the two uh, first order dark fringes, right? The one on the left and the one on the right side of the central bright fringe. Okay, that is what is meant by capital Y. So if we divide that by 2, then we are talking about capital Y sub M, which is the distance between uh, the first order dark fringe on either side of the central bright fringe, all right, to the center of the central bright fringe. That's why Y sub M is equal to 1 half the value of capital Y. That is, Y sub M is equal to 5.22 raised to the negative 2 meters, then divided by 2. So we get the value of capital Y sub M equal to 2.61 raised to the negative 2 power meter. We use this equation, capital Y sub M equals x times m times lambda over a, right? For us to be able to calculate for our target variable, small letter a. So x, as earlier defined, is the distance between the slit and the screen. Small letter m, okay, represents the order of the dark fringes. In our problem, we're talking about the first order minimum or dark fringe. And of course, lambda is the wavelength of the incident light, which is, of course, emitted by a monochromatic source, right? And our target variable, which is denoted by small letter a, is the width of the aperture or the slit, right? Which may also be considered as the thickness of the human hair strand used, okay, in an experiment, right? So isolating small letter a, we get this working formula. And when we substitute the given quantities, we get a equals the product of the value of x, which is 1.25 meters, times the value of uh, the first order minimum equal to 1. And then the wavelength lambda, 6.328 raised to the negative 7 meters. And then divided by the computed value of capital Y sub m, 2.61 raised to the negative 2 meters. So when we do our math, okay, we arrive at the value of small letter a equal to 3.03 raised to the negative 5 meters, which of course, when converted to nanometers, we get A equals 30.3. I should say, when converted to micrometer, the value of A is equal to 30.3 micrometers. All right, which represents uh, the thickness of the human hair strand used in the experiment. All right. So we are able to compute for the thickness of the human hair strand, all right, using this method of single slit Fraunhofer diffraction of light. So on these notes, may I say, mabuhay. Till the next episode, MashaAllah. Thank you very much for your indulgence. Please don't forget